Hello, everyone. Let's now study bad limits of the form either 0 to the power 0, 1 to the power of infinity, or infinity to the power 0. Those are the bad exponential form. Oh my God. La misère. All right. So let's just start with the most basic example of the advanced exponential form, bad exponential form. Let's compute the limit as x approaches 0 plus of x to the power x. So if you just replace x, as usual, you just replace x by 0, but what do you get? You get 0 to the power 0. This is bad because normally in algebra, if you have 0 to the power of anything, you're going to get 0. If you power anything to the power 0, you need to get 1. So what is 0 to the power 0? You just don't know. It's a bad form. So when you get a 0 to the power 0, bad exponential form. So what do you do? So the trick here, even if those are the hardest limit you're going to be playing with, the steps to solve these problems are always the same. So to some extent, these questions could be seen among the easiest one, because if you follow the steps, you're going to get to the answers. Okay, so here what you do, poof. So the big trick here for that one is that if you have 0 to the power 0, or 1 to the power of infinity, or infinity to the power of 0, you need to use the following fact, that a is the same as e to the power of ln of a. So you're rewriting a in a very weird way. Okay, so I know it's weird, but this actually works. Like, for example, when I go out into a bar and I just approach a barman and I say, hey man, I'm e to the ln of 52 years old. Of course he freaks out. Like he doesn't understand I'm just trying to say that I'm 52 years old, but he freaks out. He calls the bouncer and says, hey, this guy's freaking me out. Can you kick him outside? So they bring me outside, they kick me, and they beat me up. But that was part of my plan. I like to be roughed up sometimes. So play guess. So I won in the end. Okay. So yes, I'm e to the ln of 52 years old. So, and the reason why you're doing this is that the e ln of your expression, if your expression is a bad exponential form, it will break that exponential link. What do I mean by this? So if you look at our question, so we have x to the power x. So the first step is to introduce an e ln. So here, what happens? So if we go, poof. So here I'm rewriting the exact same thing. So x to the power x is the exact same thing as e to the power ln of x to the x. And now what happens is that the exponent of x to the x will go down up front. So here you can bring the exponent down. The x will fall down with this logarithmic property. If you have ln of something to the power something, that power can come down as a coefficient. So now what you get is a brand new limit. Okay, not a brand new limit, but you can rearrange your limit the following way. So as x comes down in front of the ln, you get the following. So here the x falls, so poof, you get the limit as x approaches 0 plus of e to the power x ln x. And now what happens if you replace x by 0? Of course you can't, because you get 0 plus ln of 0, which is bad. But then poof, if you replace x by 0 plus, you're going to get 0 plus times ln of 0 plus. 0 plus is 0, and ln of 0 plus is minus infinity. So boom, you're going to get 0 times minus infinity, which is a bad product. So here the idea is that every time that you have a bad exponential form, and then you introduce e to the ln, you're breaking that relationship, and you're always going to get a bad product. So what you do is you just set up a different limit on the side that will just deal with that limit. If you can figure out the green part, if the green part goes to 5, then your answer is E5. So you set up this brand new limit. Where you're only going to focus on the exponent. Okay, so here we go. So poof, I have a brand new, let's follow the arrow here. I'm going to call this new limit the star limit. So if you set up here the limit as x approaches 0 plus of x ln of x, of course we know it's a bad product because we just checked it. So we know we need to flip one of the two terms. And of course, because of the trick, which is introducing e ln, the second term will always be a logarithmic term. And then this goes back to that trick when we saw bad product. If one of the two terms is a ln, you never flip a ln. So you bring the x downstairs and you get this limit, ln of x over 1 over x. If you replace x by 0 plus, because we have no choice, you get ln of 0 plus, which is minus infinity, over 1 over 0 plus, which is infinity. Now we have our bad product. So now we can apply Hospital rule here. So if you apply Hospital rule, so the derivative of ln of x will be 1 over x, and the derivative of 1 over x is going to be minus 1 over x squared. So poof, I'm applying Hospital rule, differentiating the ln, differentiating the 1 over x. If you rearrange those two fractions, you're going to simplify this as minus x. If you replace x by 0, you're going to get minus 0, which gives you 0. So now you can go back to your exponent, x ln x. And now that it's freshly computed, you can replace, boom, that x ln of x by 0, and then e to the power 0 is just going to be equal to 1. So here all that work for the exponent that we did on the side leading to 1 tells us that the original limit goes to e to the power 0, which is 1. And here I really want to stress the fact that these bad exponential form, they always follow the same path. You introduce the trick, so you have an algebraic expression A, you go e ln A. And then this ln is going to break the relationship. It's going to bring the power down, and you're going to always get a bad product of the form 0 times plus or minus infinity. And then the thing that freshly falls will not be a logarithmic term, and that's the one you're going to flip to get a bad quotient of the form 0 over 0 or infinity over infinity. Then you apply Hospital rule, you clean up, you reapply if needed. In this case, only one application of Hospital rule, we got 0. That's the power of my e for my final answer. E to the 0 in this case gave me 1. But the steps are always the same. Introduce the trick, e ln A, bring down the exponent, focus on your product, the exponent that freshly flips, bad quotient, Hospital rule, and then you have the limit for your exponent. So it's always going to work. These are the toughest limit, but the structure of the solutions are always the same. And we'll do another example to really illustrate that fact. All right, let's do another example, the toughest of the toughest. Let's compute the limit as x goes to infinity of cosine of 1 over x, all of that to the power x squared. As usual, let's just replace all the x's by infinity. You get cos of 1 over infinity, which is cos of 0, and cos of 0 is 1. And then for the power, you get infinity squared, which is infinity, and 1 to the power of infinity is bad. So let's use the trick. So we have our original limit, and now we're going to introduce the trick. So the trick says, let's introduce an e ln in it. So we have an e ln, and now what will happen when you introduce the e ln to your expression, the x squared will go up front as a coefficient. So you get a brand new limit, x squared ln of cos of 1 over x. And if you take the time to evaluate x by infinity, you're going to get, so if you replace every single x by infinity, you get infinity squared, which is infinity. So you get your infinity for the first part. And now for the cosine, you get 1 over infinity, which is 0. Cos of 0 is 1, and ln of 1 is 0. So you get your bad product. So what we need to do is we need to figure out, okay, what is the limit of x squared multiplying ln of cosine of 1 over x. So we set up this side dish limit computation. I'm going to call this the star limit on the side. So let's compute the star limit. So as usual, the power that just freshly fell down from the trick will go down, okay, as 1 over x squared. So you get this brand new limit, and of course you can double check it, but if you do replace x by infinity, you're going to get what? Well, you're going to get, here I'm just going to state it, but you're going to get cos of 1 over infinity, which is cos of 0, which is 1, ln of 1 is 0, and 1 over infinity squared is 1 over infinity, which is 0. So you get your bad 0 over 0. Now you have the green light to get to use hospital rule. So here, a lot of work, a bit of chain rule here. So the ln of cosine of 1 over x, so we have the ln of something. So you get 1 over that something times the derivative of the inside. Cos of something is minus sine of that thing times the inside derivative, which is minus 1 over x squared. And down there, 1 over x squared is x to the power minus 2. So you get minus 2x to the power minus 3, also known as minus 2 over x cubed. I'll let you simplify these two fractions, but when you do, the numerator will become x sine of 1 over x, and the denominator will be minus 2 cos of 1 over x. And here I'm going to be very lazy, okay, because I know from a previous example at 5.5.12 that when x goes to infinity, the limit of x sine of 1 over x is simply going to be equal to 1. So I'm not going to push it more. I'm just going to know the fact that I know where the numerator is going. It's going to 1. So you're going to get 1 over minus 2 cos of 1 over infinity, which is cos of 0, which is 1. So you get minus 1/2. So all that crazy work at the exponent to get minus 1/2. Now, if you go back to your original limit, we just figured out that the limit of the power is minus 1/2. So the original limit goes to e to the power minus 1/2. And then if you're really fancy, you could leave it like this, of course, but if you're really fancy, that's 1 over e to the 1/2, which is 1 over the square root of e. So this very nice limit here, again, impossible to guess, okay, 1 over root of e, that's a very crazy number. And in terms of difficulty, this is clearly the toughest type of limit you would get. The toughest type of bad exponential limit, where you have to do a lot of work at the exponent to get to the final answer. In general, you'll get like anything in between from the easier example, x to the x, to the craziest example, cos of 1 over x to the x squared. But I really want to stress the fact that if you follow the steps, so you found out just by plugging infinity here in this example that this was a bad 1 to the power of infinity, which is a bad exponential form. So you use the trick, you introduce an ln to destroy this exponential relationship. The power, the x squared, fell down in front of the ln of cos of 1 over x. That power that freshly fell down, if you just study the exponent, will be the one that you flip in your side dish limit to get the bad quotient, to apply Hospital rule. In this case, I was able to recycle some of the computation from a previous example, but whatever. In general, this is where, like in the exponent, after you flip, like the exponent of the exponent, you use the Hospital rule once or twice or a couple of times to figure out where is the exponent going, and then your final answer is e to that exponent. Okay, so the steps are always the same. The level of difficulty, of course, varies, but it's always the same. But now we have all the tools to attack every single limit. There's no longer any limits that we cannot do thanks to Hospital rule in this class. Okay. All right. For that section /chapter, that's it. That's all. Bye-bye.